Good morning everyone. So, we are looking into the various problems of macroscopic balances when we will be having a stationary frame of reference, a moving frame of reference with constant velocity and moving frame of reference with acceleration, and we will be doing some more problems today, and today is the last class. So, basically I have a host of problems from the exercise of your book, and I think these problems are quite interesting, and it will be worth to look into these problems, how to solve them. Okay. So, you can expect couple of problems in your final examination based on this. So, the first problem we will be attempting is problem 4.134. That is given that it's a there is a road, and where a cart is moving frictionless. Okay, its mass is m, and the friction between the surface and the wheels is there is no friction. Okay. Now, initially the cart was moving in the right direction into this direction, this positive x, this positive y, with a uniform velocity u naught. Okay. Now, suddenly at time t equal to 0, from the two nozzles water jets are striking on the front part and the rear part of the cart with the same velocity v, and the nozzle cross section area is A. Now, you have to find out, there will be a transient of velocity profile, velocity will be existing in the cart, and you have to obtain a general expression of acceleration as a function of time. Once you know acceleration as a function of time, you can find out velocity as a function of time. So, you have to you can take a control volume around the cart, okay, and this positive x, this positive y, and in this control volume a water jet is entering with velocity v and area A. So, you will be with respect to the control volume, the at any point of time the velocity of the cart is u. So, relative velocity of this stream entering is u plus v in the negative x direction, that is important, and this one will be v minus u in the positive x direction, the velocity component, okay, relative velocity. So, this is v 1 relative, v 2 relative, and this is a, and this mass is m. So, you can write down the x component equation of motion . And the problem is given that the amount of water that is sticking to the car is negligibly small. Okay. So, you just write down the general expression m du dt. All the other external forces will be equal to, there is no friction, there is no frictional external surface force. Since it is open to atmosphere, the pressure is acting from all the sides. So, there is no pressure force. So, what is left behind on the left hand side of your equation of moment motion, that will be minus m du dt is equal to, that local derivative will be 0, because there is no mass of water that is sticking to the car, cross section area, the net flux, there is u relative in the x direction rho v dot dA. Okay. So, this becomes minus m du dt. Now, the surface number 1, now relative this velocity u x is nothing but v plus u, because u is in this direction, v in the opposite direction with a minus sign, because in the negative x direction. So, it becomes minus v plus u rho v plus u. Now, the area normal is in the opposite direction to the velocity that is coming. So, there will be negative sign because of that, okay, minus a, and the phase number 2, this let us say phase number 1, this is phase number 2, that is v minus u in the positive x direction rho v minus u times area with a negative sign, because area normal is the outward area has a direction outward normal and velocity in this direction. So, there will be again a minus sign here. Okay. So, finally, you will be getting, so there will be, this term will be positive, this whole term will be negative. So, it will be rho times a u plus v whole square minus v minus u whole square. So, this is nothing but 4 rho a u v. Okay. So now you have to take u on the other side and carry out this integration. Du by u is equal to minus 4 rho a v by m dt, and at time this has to be integrated from t equal to 0 to any point of time t. At t equal to 0, it was having a velocity u naught, that is uniform velocity, and time t its velocity is u. So this becomes ln u by u naught minus 4 rho a v m times t. So this minus you can take this side, and this will be ln u0 by u. Okay, whatever. So u will be having a functional form u naught exponentially minus 4 rho a v by m times t. Okay. So that is the general expression of u, and at time t tends to infinity, this velocity becomes almost 0. Okay. Now you can find out what is the distance it has traversed as a function of time. You can replace dx dt by u by dx dt, u0 exponential minus 4 rho a v by m into t. So you can carry out this integration. So it becomes u0 exponential minus beta t, where beta is 4 rho a v by m, and this becomes 0 e to the power minus beta t dt from 0 to t. Let us say from at time t equal to 0, it was a location x equal to 0, and at any x at any time it is t. So this is u0 minus 1 by beta e to the power minus beta t minus 1, or u0 by beta 1 minus e to the power minus beta t. Okay. So that is the is problem number 134. So we will move to the next problem. Okay. So the next problem is 117. Again, it is an exercise problem. There is from a nozzle, a jet of water is issuing out, and this area is given as 7.85 into 10 to the power minus 5 meters square with a velocity 25 meter per second. Okay. Now it hits a block with a vein splitter. So there is a vein something like this, and this angle is 30 degree with horizontal, and this 90 degree. Okay. This is something like this. This issuing out vertically with a mass flow rate m2 dot, and in this direction the mass flow rate is m3 dot. So basically some stream is falling on this vein, and this block is moving with a constant velocity u is equal to 10 meter per second towards right. Now this amount of water, that is let us say m dot 1, that will be splitting into two parts, m2 dot and m3 dot. Okay. And this angle is 90 degree, this part is vertical. Now you have to find the ratio of the mass flow rate of water m2 dot by m3 dot required to produce 0 net vertical force on the splitter vein. This is known as the splitter vein, it splits the trim. That will be part 1. Part B is determine the horizontal force that must be supplied to maintain the constant speed of the splitter vein 10 meter per second. It must be applied to maintain the constant speed of the vane. Okay. So, you select a control volume about this. This angle is 30 degree, only this portion, and this is just going out, issuing out. This is M3 dot and this is M2 dot, and let us say it is M1 dot. Okay. So, from the overall material balance you can say that M1 dot is nothing but M2 dot plus M3 dot. Okay. And what is M1 dot? M1 dot is nothing but, what is M1 dot? Rho u relative, because this whole system, this whole control volume is moving to the right with some velocity. Okay. So, it is u relative times a 1, that is M1 dot, right. What is u relative? U relative is nothing but v minus u. There is given v is 25 meter per second, u is 10 meter per second. It is basically M1 dot can be found out from this 10 cube, u relative is 15 meter per second into A1 is given as 7.85 into 10 to the minus 5 meter square, and it turns out to be it turns out to be 1.1775 kg per second. Okay. Now, the first part, there is no effective vertical net force. So, you have to do a momentum balance in the y direction and put that equal to 0. So, y momentum balance is basically Fy is cross section. So, right, Uy, that is relative velocity in the y direction, rho v dot dA. Now, there are three points of where the liquid intersects the cross section of the control volume. This point there is no y component. This point everything is in towards the y component. There is no component. There is the full component is in the y direction, and in this part, point number 3, there will be sin 30. Half of the will be in the y direction. Rest of them will be in the x direction. So, if you do that, it becomes u relative, uy relative. Anyway, that is relative velocity that we have already found out. This is M2 dot minus uy sin 30 M3 dot. This rho v dot dA is nothing but mass flow rate. This is at point number 2, this is point number 3. So, this should be equal to 0. So, whatever the value of uy, it will be get cancelled. So, you will be getting M2 dot is nothing but M3 dot by 2. So, the ratio is nothing but 1:2. Okay. Now, from the material balance, you have M2 dot plus M3 dot equal to 1.1775 something. So, M3 dot becomes 0.785 kg per second. That can be evaluated. Okay. In part B, you have to find out the net force in the x direction. So, it will be rho ux square A1 plus ux cosine 30, that is in x direction, times M3 dot. Here velocity and area will be in the opposite direction. Here the velocity and area will be in the same direction. At point number 2, since it is vertical, there is no horizontal component. At point number 2, there is no horizontal component because it is issuing out vertically. So, just substitute the values. It turns out to be 10 cube into is 15 square. So, it is 225 into 7.85 into 10 to the power minus 5 plus 15 cosine 30. M2 dot you have found out, that is M3 dot, it is 0.785, and this value is 7.66 Newton. So, you have to supply a force in the negative x direction to counter in the positive x direction to counter this force. Okay, so the force that has to be applied from outside on the control volume will be 7.66 Newton in the positive x direction to counter this one. Okay. The next one is problem 123. You have a tank, there are two wheels, it moves frictionless on the surface and there is a water level in it, and this whole at the bottom point there is a nozzle of area A, and by which the water jet is issuing out with a velocity v relative to this cart. Okay. And as a result this moves in the positive x direction, let us say towards right with a velocity u at any point of time. So, v is basically the relative velocity of a jet issuing out. Now, initially you are having m naught of mass of water inside the cart, and now your this portion is pressurized, so that we can consider this velocity will be almost same over a period of time. Okay. So, we have to find out, obtain an expression for speed of the cart as it accelerates from the rest. Okay. So, around the cart you draw a control volume, and the velocity of water, this is the relative velocity, this v is relative velocity between the with respect to the control volume. Okay. Now, we select the coordinate system towards left, let us say it is x direction, and this y direction. You write down overall material balance. In overall material balance, it is d dt of rho dv, where this integral is over control volume plus control surface rho v dot dA. Now, at any point of time the mass is, let us say, m of the control volume. So, it is dm, it is nothing but dm dt plus rho, this v is directly negative in relative velocity. So, you need not to write it v minus u, it is given in the problem, it is the relative velocity directly, because this is not measured, this v is not measured from the fixed frame of reference, it is measured with respect to the moving frame of reference. Now, so v and area direction of normal to the area, they are in the same direction. So, there is no negative signs. So, it will be rho v a is equal to 0. Okay. So, you can integrate this out, v is constant, and find out how much mass is left after a point of time t. Okay. So, dm dt is nothing but minus rho v a, the right hand side is constant. Initially you are having a mass m naught, now you are having a mass m. So, it is nothing but m at any point of t is nothing but rho v a t. Okay. Now, you can write down the x component momentum balance, its frictionless, surface is frictionless. So, your equation becomes minus a x v relative times rho v a, because there is only one point of that is where the water is going out, v relative square rho times a, right. It is basically integral of cross section v relative in the direction, in the x direction, times rho v dot a dA. They are in the same direction, so there will be, it will be of positive sign. Now, this is nothing but m du dt is equal to v square rho a, and now this m is at any point of time. So, you just put the expression of m, that is m0 minus rho v a t du dt is equal to v square rho a, and now you take it to the other side. Dt. At time t equal to 0, the velocity was 0. At time t equal to t, its velocity is u. Okay. So, there it will be in terms of some logarithmic a function on the right hand side, and the final expression you will be getting after the integration is nothing but u is equal to v ln m0 minus rho v at t divided by m0. Okay. So, you can put the values and evaluate the value of velocity at any point of time, or if you would like to find out the how much distance it has traversed, you just replace it u by dx dt and carry out this integration. Problem 4.124, it is basically again the vein problem. Vein and cart problem. Water jet is heating up it with a velocity v, density rho, and area of cross section of jet is a, and the whole assembly is moving towards right with u. The vein angle is theta. This is a frictionless surface. Okay. Now, the acceleration of this, initially it was at rest and now it started accelerating. Now, the acceleration of the cart is controlled by changing this vein angle. I would like to control the acceleration, I have to maintain the acceleration of the cart to be constant by changing the vein angle. Otherwise the acceleration will be function of time. Now, it is assumed that there are two ways. Either you change the vein angle or you change the area of the jet with as a function of time, so that the acceleration will be maintained at constant speed, constant rate. Now, for this particular problem, acceleration of the cart is maintained constant by changing the vein angle theta. Okay. And constant acceleration is given as ax is nothing but 1.5 meter per second square. I would like to maintain the acceleration of this cart at 1.5 meter per second square by changing the vein angle theta. Okay. Now, area is 0.025 meter square, v is 15 meter per second. The cart vein assembly has a mass of 55 kg, neglect friction. Now, we have to find theta as a function of time. Okay. Suppose it is possible the vein angle is changed at every, it will be a function of time to maintain the acceleration at constant rate, constant value 1.5 meter per second square. Now, obviously theta will be changing as a function of time. Now, you have to find out that theta as a function of time and value of theta at certain point at t equal to 5 second. Okay, that is the problem. So, you select a control volume about the cart vein assembly. So, this is a control volume. This is point 1 where velocity is coming in, this is point number 2 where velocity was going out, and this whole assembly is moving towards the right with an with a velocity u, and we fix our coordinate system x towards the right and y as usual. Now, the relative velocity, then equation of material balance, overall material balance says that V1, that is relative to the control volume, is equal to V2, right, because the jet cross section, the vane, the area of the jet of the vane remains constant. So, that is nothing but V minus u. This is coming absolutely with a velocity v and is moving at any point of time u. So, at any point of time relative velocity is v minus u. Okay. So, you have to do an x momentum balance. There is no external force, no friction force, pressure is acting from all the sides. Now, section 1 velocity and area normal are in opposite direction, section 2 they are in the same direction. So, it will be minus rho v minus u whole square a plus rho v minus u whole square cosine theta times a. Cosine theta is the x component at the point exit point, point number 2. So, your max becomes rho v minus u square a into 1 minus cosine theta. Now, we would like to maintain this area acceleration to be constant at a value 1.5 meter per second square. So, acceleration is constant, means that is at 1.5. So, this is nothing but du dt, right. So, u as a function of time becomes 1.5 t, because at time t equal to 0 there was no motion. So, u equal to 0 at time t equal to 0. Substitute there, you will be getting an expression of theta as a function of time. So, max becomes rho v minus u whole square a 1 minus cosine theta, and 1 minus cosine theta becomes x rho a minus u square, u becomes 1.5 t. So, cosine theta equal to 1 minus x rho a minus 1.5 t square. This is constant because you are maintaining constant acceleration. So, theta will be cos inverse of this. Now, if you put the values, it comes out to be 19.72 degree. Okay, so there is a little variation in this problem. In the next problem, the second possibility was there, that is problem number 100. The next, just immediately next problem 125, it says in the same assembly, in the same system, we would like to maintain the constant acceleration by programming the jet area as a function of time, where vane angle is fixed. Now, we have to find out area change as a, what is the desired programming of area change as a function of time. That means, how the area is varying, area of the jet is varying as a function of time, and then it asks at a particular point of time, let us say 2 seconds, what is the area. So, there are so many variations of the same problem. That is problem number 125. This is 120 degree, this is in obtuse angle. So, this angle is 60 degree. Okay, that is the vane, this is the cut, and here the rho is 10 cube, let us say 10 cube kg per meter cube, v is 10 meter per second constant, and area is a function of time. Now, since we are maintaining a constant acceleration, acceleration of kart is constant at 2 meter per second square, that we would like to maintain the value. Now, area, this is accomplished by programming water jet area AT reaches the cart, jet speed remains constant at 10 meter per second. We have to find an expression of area as a function of time and the value of area when t is equal to 2 seconds, and this whole assembly has a mass 3 kg. Okay. And at any point of time we assume that it is moving in the right direction with a velocity u. So, it is exactly the previous one, like max is the acceleration net force on the left hand side minus rho v minus u whole square a. Okay, we take a control volume like this. This is v relative, this is a positive x, this is y. But in this case, since this angle is obtuse angle, the velocity, the x component velocity is in the negative x direction. But since velocity and area normal to the area are both in the same direction, so the product rho v dA will be having positive sign. So, you have to be very careful about the sign, that is the only thing, and you have to take a proper control volume. Plus minus v minus u, that is in the negative x direction, cosine theta rho v minus u a. This will be positive because in the same direction the normal, area of the normal and velocity at that point number 2. So, it becomes max is equal to rho v minus u square a 1 plus cosine theta. And a becomes max rho v minus u square one plus cosine theta. Now, since ax is constant at 2, so and it is starting from rest, u will be function of t, right, that you have to substitute here and find out the value. So, area as a function of time becomes max rho v minus 2t square 1 plus cosine theta. Now, if you put the values and evaluate at time t equal to 2 seconds, this area becomes 111 millimeter square. Now, in the 4th edition of Fox and Bagnall, all most of the answers are given, all the problems, 4th edition, but the previous edition they have given the answers to the even number of problems. So, that you can check the answers whenever you will be doing the solving some problems from the exercise as practice. Then the next problem is very interesting, that is problem number 126. There is a rocket sled, it is basically a cart moving at high speed. Over a rail, this is the rail, and at the front it has a vane sort of, it is called a scoop. So, it is basically a vane. Okay. Now, it is lowered. So, between the 2 rails there is water, it is coming at a very high speed, let us say some very high speed. Now, it has to slow down by lowering the scoop into the water, where that will offer some kind of resistance. So, there is in this particular problem, that it has an initial speed 300 meter per second. It was coming with an initial speed 300 meter per second, and it lowers the scoop into water to slow it down, and the scoop is 0.3 meter wide. It is basically a blade whose width is 0.3 meter, okay, and it deflects water through 150 degree centigrade. So, water enters, takes up right, and this angle is 150 degree. Okay. Scoop is 0.3 meter wide, water deflects through 150 degree. Now, the trough is 800 meter long, it has to be stopped by covering a distance 800 meter, because that is the trough in the front, it is available. Okay. So, the length is 800 meter before that is available before coming to a halt. This mass of this whole assembly is 8000 kg. Okay. Now, the aerodynamics drag force that is in the opposite direction of the motion, that is F d is u square, k times u square, then k is equal to 1 for this particular problem, u square. Now, it is desired to slow down the sled to 100 meter per second, it is not to come to a stop, because by traveling 800 meter we would like to reduce the speed to 100 meter per second. You can solve the problem when it comes to stop as well. Okay. For this particular problem, u final after traversing 800 meter is 100 meter per second from 300 meter per second. Now, we have to find out the depth by which the scoop has to be lowered in the water, so that this can happen. That is a very good design problem, right? You have to lower down the scoop to break the car, so that its velocity reduces from 300 meter per second to 100 meter per second. Now, how much water in the how much of depth of this scoop has to be lowered in the water level? Okay. So, at any point of time, if u is the velocity of this cart, then the relative velocity of water that is moving through vein is u with a negative direction, because water will be coming in this way and it will be going out with a velocity u. Okay, that has to be recognized. So, what you have to take? You have to take a control volume the whole assembly, and let us say this is positive x direction, this is positive y direction, and velocity is u at any point of time. Okay. Now, you write down the x component equation of motion or x component momentum balance, then it will be f x minus m du dt. There is no pressure force, it is acting in all directions, neutralized. The f x is basically surface force, cross section u relative rho u relative times dA. Okay. Water is entering here, it is coming out there with an absolute velocity u relative to the control volume. Now, in this case it is minus u, because it is negative x direction, and area normal is also in the opposite direction to the velocity of entering water. In this point, at this point, velocity direction of u is positive, component is u cosine 30, that is in the positive x direction, rho times v dot a will be having a positive direction, because they are in the same direction. And f x will be, what is f x? F x is the external surface force that is acting on the control volume. What is that? Drag force. So, it is minus f d, because drag force is opposite in the negative x direction. So, you just write it down, f d minus u m du dt is equal to rho u square a 1 plus cosine 30. Okay, I am just writing the final. If you break down these two parts, it will come out to be rho u square a 1 plus cosine 30, and minus m du dt becomes, this is nothing but k u square, k is equal to 1 for this problem. So, it becomes rho u square and k is equal to 1 for this particular problem, given in that problem, k rho u square a cosine 1 plus cosine 30 plus u square, right. So u square rho a 1 plus cos 30 plus 1. Okay, this can be brought in the denominator. Now du dt, the acceleration can be replaced by u du dx because the distance is given. Okay, so u square rho a 1 plus cosine 30 plus 1 over m, 1 u will be cancelling out, yes. So 1 u will be cancelling out, and finally you will be getting which one? The m will be common, whole thing, it is under the whole thing, let us come. So you will be getting finally minus du by u rho a 1 plus cosine 30 plus 1 the whole divided by m dx 0 to x, and it is 300 meter per second initially at time t equal to x equal to 0, and it is some value 100 meter per second at any point at the when x equal to L, that is 800 meter. So it is minus ln u by u naught is equal to rho a 1 plus cos 30 plus 1 divided by m times L. And what is area? Area is nothing but the W times D, right? Since W is given, you can find out what is the depth. Now you have to put the values, and this depth becomes 17.9 millimeter. So basically you have to lower down, if you put the value, it will come out to 18 millimeter. So if you lower down 18 millimeter of the scope inside the water level, then this can happen. You can solve this problem, how much depth has to be lowered of the scope so that it will come to a halt within 800 meter. That can be solved as well. Okay, I will solve couple of problems. Problem number 127, the next one, that is an easy one. You have a cart, there you have a vane at the back side, this frictionless ground, where it receives at the horizontal level and it discharges water at horizontal level around 180 degree bend. So from a nozzle, a water jet is falling on this with density rho v, velocity area a. It was initially at rest. Starting from rest, the cart is propelled by a jet. That is the problem. Jet strikes a curved surface and makes 180 degree turn. Okay, this mass is 100 kg, area is 0.001 meter square. The jet maintains the area. Velocity of the jet is 30 meter per second. Find the speed of cart after 5 seconds of start. Okay. So you take the control volume, the whole thing, take the positive x, y, it enters with a velocity u relative, which is nothing but v minus u, comes out with the same velocity to maintain the material balance only. in the opposite direction, okay, and there is no friction. So, my left hand side of the x momentum will be having the acceleration term minus rho u relative square times a, because direction of area normal is outside, velocity is inside, plus minus u relative, because since it is 180 degree, so it is in the negative x direction, rho u relative a, this is positive because the area normal is in the same direction of the velocity that is emerging out of the port 2. So, it is nothing but minus 2 rho u relative is v minus u, right, v minus u square times a, that is it. So, m du dt is 2 rho a v minus u square. Now, you have to carry out the integration. Once you, so it is basically du v minus u square 0 to u is 2 rho a by m dt. Okay. So, I am just writing the final expression. It comes out to be u by v is 2 rho a v t divided by m plus 2 rho a v t. Okay. Put the values at time t equal to 5 second, the u comes out to be 22.75 meter per second. Now, next problem, it says that in the for this problem number 127, you have a drag force which is proportional to velocity square. Now, since there is a drag force, now there will be terminal velocity. Before attaining the terminal velocity, the velocity will be varying with time following some expression. So, find out that and find out the terminal velocity. So, f d is nothing but k u square, and you are having minus k u square minus m du dt. It is in the opposite direction, that is why this negative term appears, minus 2 rho v minus u whole square a. So, finally, you will be getting a x as 2 rho v minus u whole square a minus k u square divided by m. That is the expression of acceleration, whole thing, whole divided by m. This says find a acceleration when u is equal to 10 meter per second. Just put the values and it will turn out to be 6 meter per second square. Now, we can find out the terminal velocity. The terminal velocity will be when ax is equal to 0, then u will be replaced by u terminal. One plus k by twice rho a. Okay. So, that is the terminal velocity. You have to put the values and find out the numbers. Okay. So, you can find out how much distance it has covered before attaining the terminal velocity. That can be also done. In that case, what you have to do? You have to write down this equation as u du dx. Okay. And the limit of the integration will be from 0 to t final, and limit of this will be from 0 to u terminal. Okay. The next one, I will just solve one more one, no problem. So, it is a cart van assembly again, and it is moving with a velocity u initially. Okay, the initial velocity of this assembly is u naught towards the right, and let us say this is x, this is y axis for this particular problem. Now, at time t equal to 0, a jet starts falling on this cart from this direction with a velocity 8.25 meter per second and area 900 meter square. Okay, 900 millimeter square, and this angle is 60 degree. Now, we have to find out after what time and distance the cart stops. Well, it will be coming in the opposite direction, then it is impeding the motion basically. So, it has to stop. Cart stops. Okay. So, again you have to take your control volume including the whole assembly, and the water exit point is point number 2 with u relative, and here it is u relative. This is in the positive x direction, this is also in the positive x direction. Velocity and normal will be in the opposite sign here, they will be in the same sign there at point number 2. We have selected our coordinate system. This is positive x, cart is moving in the negative x direction, it stops in the, so instead of acceleration it is basically deceleration problem, right, it is basically decelerating. So, ax will be replaced by minus ax because u is in the opposite direction, because we have taken the positive x in this direction, the u is having in this direction. So, it is deceleration. So, in your x component balance, it is everything else is frictionless, m minus du dt, because it is deceleration. Okay. So, it becomes v plus u minus rho v plus u a, that is point number 1, that is entry point, and this is the exit point v plus u, the relative velocity is v plus u cosine 60, that is the exit point, rho v plus u times area normal and velocity in the same direction. So, it becomes rho v plus u square a plus rho v plus u square a cos 60. So, minus m du dt becomes rho v plus u whole square a 1 minus cos 60. Cos 60 is half, so it becomes rho a by 2 v plus u square. So, v plus u to the power minus 2 du will be rho a by 2m dt 0 to t. There will be a minus sign here, and this integration will be from u0 to 0 and 0 to 0 to t before it stops. Now, if you carry out this integration, the final form will be u0 by v plus u0 rho a time divided by 2m, and t becomes 2m u0 rho a v plus u0. Okay. If you put the values, t comes out to be 1.7 second. And the distance, for that you will be replacing ax by u du dx. Instead of writing du dt, you have to express that. So, it comes out to be minus m u du dx is rho a by 2 v plus u square. That is the governing equation, and you will be having u plus v whole square du equal to minus rho a by 2m dx. U0 to u equal to 0, that is the final one before coming to stop, and the length it will cover is L. And I am not solving the problem for you, you do the couple of steps by yourself. The final expression of length becomes 2m by rho a u0 by u0 plus v plus ln u0 plus v by v. Now put the values of different quantities on the right hand side and estimate the length or distance it will travel because coming to a halt. Okay, I had one more problem, but that is a solved problem in your book. It is a rocket propulsion problem. In that case, a small rocket accelerates vertically up from rest. Okay, air resistance is negligible. Rate of fuel consumption is given it at constant rate. It is 5 kg per second m dot out. Because of that, exhaust velocity is 3500 meter per second relative to the rocket. Okay. Now we have to find out the acceleration of the rocket and velocity after some time. Let us say time t equal to 10 seconds. Now what you have to do, it's basically you have to put a y component equation of motion and write down the y component momentum balance. Okay, and since the fuel is coming out at a constant rate 5 kg per second, you have to do a material balance as well to find out whatever the mass that is remaining in the rocket at any point of time. Now whenever you are compiling the y component equation of motion, the mass will be mass of the control volume remaining at point number at time t will be replaced whatever is you will be obtained from the material balance. Then you have to integrate out. It is a solved problem in your book. So if you go step by step in the example, so you can understand it. Okay, fine. Thank you.